In a course on real analysis, you would have seen many instances where we had to extend our given function, which is defined on an interval, to a larger interval. So, a function f defined on I had to be extended to a function on j containing I. In fact, if we started off with a continuous function, we would have demanded many times to get hold of an extension which was also continuous. If we started off with a smooth function, the requirement was that we get a smooth extension to j. So, the regularity had to be preserved. In this lecture, we will address a similar problem for holomorphic functions. Holomorphic functions, as we have already seen by now, is a very rigid class of functions. So, it is not very easy to answer the question of extension. Many times there won't be an extension possible at all. There are functions, for example, defined on the unit disk, which does not extend past the boundary at all. So, in this lecture, we will prove a theorem called the Schwarz reflection principle, which tells us certain special circumstances when we will be able to talk about the extension of a holomorphic function. So, let us try to set up the circumstances where we can indeed talk about such an extension. Let omega be an open connected set. And we will define omega bar to be the set of all those points z in the complex plane such that the conjugate of z belongs to omega. If we have a function f which is holomorphic on omega, you can get a corresponding function defined on omega bar which is holomorphic as well. So, suppose f from omega into c be holomorphic. Then f star may be from omega bar into c defined, then define, let us first define f from from omega bar into c by f star of z to be equal to f of z bar the whole bar, conjugate of f of the conjugate of z. So, good exercise for you to sit down and check that f star is holomorphic because f star is holomorphic on omega bar. So, you could do it in any of the favorite ways you deem fit. You could, for example, sit down and check that the Cauchy-Riemann equations are satisfied by f star, or you could write down a power series expansion of f and get hold of a power series expansion of f star, and thereby proving that it is complex analytic and hence holomorphic. You can sit down and pick the route to establish that f star is holomorphic. Now, if omega satisfies the f star, it is not on omega, it is on omega bar, by the way. F star is defined on omega bar, as you can see here. Now, we say that domain is symmetric with respect to the real axis if omega is equal to omega bar. We say that omega is symmetric with respect to the real axis if omega is equal to omega bar. Remember that we are still in this situation where omega is an open connected set, and the connectedness will tell you, another exercise for you is to check that omega intersects the real line. What you could do is that pick a point z in the upper half plane, z bar is also in the domain omega, and because it is connected there is a path, and use the intermediate value theorem to conclude that the path should necessarily intersect the real axis. Okay. Now, suppose we will, in this lecture we will only be interested in such domains. So, in this, so we shall now focus on symmetric domains or domains symmetric with respect to the real axis. Domains omega may be open connected sets. omega which are symmetric with respect to the real axis. Now, in this scenario, let us define a function g, define g from omega to c given by g of z to be equal to f of z minus f star of z. So, let me just write it as f z bar the whole bar, that is f star of z, right. So, f star is defined on omega bar, which is omega here. So, this makes completely perfect sense, and the fact that g is a difference of holomorphic function tells us that g is holomorphic on omega. Now, suppose f satisfies the condition that f of x is a real number whenever x is a real number. Then let us see what happens to g on the points where omega intersects the real axis. Then for x in omega intersected with r, f of x bar the whole bar is equal to f of x, and this tells us that g of x is equal to 0. But then if x is in omega intersected with r, omega being an open set, we will have an entire interval which is contained in omega. Since omega is open, there exists a comma b in r such that a less than x less than b, such that ab contained in r is in fact contained in omega. Let me not complicate it too much, just say that the interval ab which is sitting inside the real line is contained in omega, and f of x is g of x is equal to 0 on AB. But then now let us go back to the previous week's lectures and recall that the zeros of a holomorphic function are isolated if it is non-zero. So, in particular, if g of x is equal to 0, if g were to be non-zero and if g of x were to be 0, then there exists a punctured neighborhood of x where g does not vanish, but that can never happen here. And the identity theorem, which it was called as, hence tells us that g is identically equal to 0 by identity theorem. Where? On omega. That is the rigidity of the holomorphic functions that we have, isn't it? And this tells us that f of z is equal to f of z bar the whole bar on omega. So, if omega were to be a symmetric domain and f is a function which satisfies the condition that it preserves the real line, then f satisfies this condition by the identity theorem. We will use this very crucially to talk about an extension theorem now, which will be proved as the Schwarz reflection principle. Before we state the Schwarz reflection principle, given a symmetric domain, let us fix some notations. Let omega be an open connected set which is symmetric with respect to the real line. Then set omega plus to be all those points in omega which are in the upper half plane. The imaginary part of z is greater than 0. Let omega minus be the set of all those points in omega whose imaginary part is less than 0. And let us denote by I the set of all those points in omega which are on the real line. Imaginary part of z is equal to 0. So then hence we have omega is the union of omega plus I and omega minus. So this is the notations that we will be using. Now let me state down the Schwarz reflection principle. This theorem is called the Schwarz reflection principle. Let omega be as above. Suppose we have a function f. Suppose f is a function which is defined on omega plus union I, complex valued function, which is continuous on omega plus union I and analytic or holomorphic on omega plus. Suppose we have a function like this. Suppose f of x is real valued for all x in I. Then there exists a function g defined on omega, holomorphic on omega, such that g of z is equal to f of z for z in omega plus union I. So in other words, it can be extended to omega minus. Let's just draw a picture. No pictures were drawn yet. So suppose this is our real line, which I am now drawing in say orange, and our domain is say something like this. So then symmetric domain, it will be something like this. So omega plus will turn out to be the region I am shading in red in the upper half plane, and the violet is the region omega minus. And our theorem tells us that, so if the light green part is I, the theorem tells us that if there is a function which is holomorphic on red and which extends to the region in green, then we will be able to extend it to the entire omega. So this is a very powerful extension theorem in the setting of complex analysis. Let's give a proof of this statement. We have already given a candidate to ourselves. When f is equal to a real number on I, then we know that f of z is the same as f of z bar the whole bar if it is defined on the symmetric domain entirely. So we will just as well define g of z to be equal to f of z bar the whole bar on omega minus, and g of z to be equal to f of z on omega plus union I. So if you notice, we have just defined g to be equal to f on omega plus union I. So in particular, g is going to match with f on omega plus union I. We just need to ensure that this function g is holomorphic. If we are able to do that, then we have a holomorphic extension of f to omega. Let's get to proving that. The first observation here is that this is an exercise again for you by the pasting lemma if you want. G is a continuous function. Crucial fact that will be used is that f of z bar the whole bar is equal to f of z on R in order to establish this exercise. G is a continuous function on omega, and enough to show that G is holomorphic. So to prove that G is holomorphic, we shall now prove that G is holomorphic on omega. If we carefully look at how we have defined G, check that f is already holomorphic on omega plus, and hence G is holomorphic on omega plus, and f z bar the whole bar is holomorphic on omega minus. So this is holomorphic on omega minus as well. So we have reduced the problem to checking for whether the function f is complex differentiable at the points on I. So enough to now check complex differentiability or rather holomorphicity on I, complex differentiability at points on I. Being a local property, what we will do is we will show that given a point on I, let Z0 be some point on I, let's prove that G is holomorphic in a neighborhood of Z0. So, in order to do that, let R be such that d Z0 R bar is contained in omega. Suppose we pick an R like this. We will show that G is holomorphic on d Z0 R, and we will prove that it is holomorphic by the Morera's theorem. By Morera's theorem, it is enough to check. So, this is an exercise for you. I will tell you why this is an exercise. It is enough to check that integral of f over, or rather g over t is equal to 0 for every triangle T in dz0R. If you go back to Morera's theorem's statement, we actually proved that if integral of g over any closed polygonal path is 0, then our function g is holomorphic. I am actually writing a more special statement here. I am demanding that we only need to check that integral of g over t is 0 for every triangular path. So, you should sit down and convince yourself that if we prove this, we are in fact proving that over all closed polygonal paths the integral is 0, and therefore, we will be able to conclude by Morera's theorem that our function g is holomorphic. Okay, so let us now draw a picture to capture what we are trying to prove. Suppose we are in this point Z0, and suppose we have the disk of radius r around. Yeah, maybe I should start off with the, and suppose this is the point Z0. So, dz0r is being captured here, and suppose we have a triangle. Suppose the triangle is like this. The first thing to note would be that we can split the triangle into two polygons, one which is being captured in red and the other which is being captured in green. And how will the arrows be? The arrows will be like this, of the straight lines where the orientation is being considered, and here it will be in this direction. And I am saying orientation, I just mean the initial and the terminal point of the lines that we are considering. So, if you notice, the green and the red will cancel off each other, and further we can split the quadrilateral below into maybe the dark green one, or some other color, maybe purple. Purple is good. So, it can be split here, and further it will be in this manner, and the red will go in this manner now. So, the triangles will all cancel off each other, and what we can conclude by this. So, this picture is representative of one particular type of triangles. There are many cases that might come up. Let me just write down what we would like to do, enough to show that integral of g over t is equal to 0 for t contained in either omega plus union I or omega minus union I, or t contained in omega minus union I. If we show it for these cases by considering the various cases that come up, and the image tells us that the integral of f over every triangle is going to be 0. So, this is enough for us to establish our result. Let us now draw a new picture in that case. So, we have now this disk of radius r around Z0, and now two possibilities can happen. Either the triangle just touches at a vertex, the part I, or it could be a triangle of this type with a edge on the real axis. There are two cases. The more difficult one is when the edge is on the real axis. We will prove that integral of f over such a triangle is 0, and I will leave the case when a vertex, just a vertex is on the real axis is there, as an exercise for you. So, we shall now prove that integral of f over t is equal to 0 when t is a triangular path. So, let me now give some names to it. This is Z1, Z2, Z3. So, when T is the triangular path, gamma Z1 to Z2 to Z3 to Z1, where Z2 and Z3 are on I. So, this is the case we will be trying to prove right now. This is the most difficult case. Once we establish this, then we are in good shape to conclude our result. So, the first observation is the following. If you notice, the convex hull T hat, which is basically summation ai zi, where summation ai is less than or equal to 1, this is a compact set, and G being continuous, G is hence uniformly continuous on T hat. So, before we use uniform continuity, let us fix some notations. Let capital M be the supremum of absolute value of G of Z when Z is in T hat. Remember that T hat is compact, and hence this is going to be a finite number. Let us call that number as M, and let D be equal to the supremum of G of Z minus G of W, where Z and W belongs to T. This is the diameter of our triangle T. So, let us set these notations, and by uniform continuity, given an epsilon positive, we have a delta. Given any epsilon positive, there exists a delta greater than 0, which is however less than epsilon. We can always do that. Delta less than epsilon greater than 0, such that the difference G of Z minus G of W is less than epsilon whenever Z minus W is less than delta. This is something on T hat. This is something which we can ensure. Now, let us go back to our picture here, and let us pick 2 points. Let us pick 2 points in dark green. Let us call the points W3 and W2 here, and connect these 2 points. Then, if we are to write down the integral, pick how are these W2s and W3s picked? W2 and W3 on gamma Z1 to Z2, yes, Z1 to Z2, and gamma Z1 to Z3 respectively, such that the difference of absolute value of the difference of W2 and Z2 is less than delta. W2 is at a distance less than delta from Z2, and similarly W3 is at a distance less than delta from Z3. This is something which we have already picked, okay. And then the integral of f over t, this is going to be equal to the integral of, where is the picture? The picture is this. This is the triangle Z1, Z2, Z3 is the triangle. By breaking it up, we can go along this triangle and then along this particular quadrilateral. The line, green line, the integrals cancel off, and we will be able to get back the integral over the triangle itself. So, writing it down, we have integral of f over t is the integral of f over the following paths: z1, w2, w3, z1, this triangle, plus, so there is an f of z dz here, the integral over gamma w3 to w2 to z2 to z3 to w3, the polygonal path of f of z dz. Now, if you notice, dz0r intersected with the upper half plane, that is an open set, and in that open set this triangle is contractible, it is null homotopic, and therefore by Cauchy's theorem this is equal to 0 by Cauchy's theorem. So, what remains is the integral over the polygon gamma w3 to w2 to z2 to z3 to w1. Let us now try to see what that particular integral is. That is exactly equal to the integral of f over gamma, right. So, integral of gamma w3 to w2 to z2 to z3 to w3. This is the let me just draw it. This is the polygon we are interested in. We have a z2 here, there is a z3, there is a w3 here, there is a w2 here, right. So, w3 to w2 to z2 to z3 to w3 of f of z dz, and this is just the sum of the integral over the various straight lines. This is from z2 to z3 plus integral from z3 to w3 from w3 to w2, and finally the integral from w2 to z2. This is precisely what this integral is going to be. We will focus on the first one and the third one together and get some estimates. If you look at f of z dz gamma z2 to z3 plus the integral of f w3 to w2, this is the same as the reversal. The second one is the minus of the reversal, right. So, this is going to be, let me write down the equation, or maybe I shouldn't jump that step, let me write it down: z2 to z3 minus integral w2 to w3 of f of z dz. We could use any parameterization of this straight line. To compute this integral, we will use the standard parameterization. So, what is gamma z2 to z3 of t going to be? The initial point is going to be z2 and the terminal point is going to be equal to z3, and similarly gamma w2 to w3 is equal to 1 minus t times w2 plus t times w3. We will do the explicit computations. We are only using the definition of the integral of a continuous function on a curve to write whatever we are writing just now. This is going to be f of 1 minus t times z2 plus t times z3. This is a straight line path. Remember, it is a straight line path and hence it is going to be smooth, and gamma prime t is just going to be equal to z3 minus z2, which is not dependent on t from 0 to 1. Similarly, the second one is integral f of 1 minus t times w2 plus t times w3 and w3 minus w2. This is precisely the sum of these two integrals. This integral is what I have just written down. So, if you look at the absolute value here, okay, let me not confuse things. Let me just look at what the absolute value of gamma z2 to z3 of f of z dz minus integral gamma w2 to w3 f of z dz. This is basically plus integral gamma w3 to w2 f of z dz, which I am just writing it this way. This is equal to the absolute value. I will just skip a step, write z3 minus z2 times the integral of f of 1 minus t times z2 plus t times z3 minus f of 1 minus t times w2 plus t times w3 dt, and then I will just add and subtract z3 minus z2 times that, and hence we will be getting w3 minus w2 minus z3 minus z2, this absolute value times the integral f of 1 minus t times w2 plus t times w3 dt. This is precisely what we will be able to write this integral as. Now we are in good shape, because if you look at 1 minus t times z2 plus t times z3 minus 1 minus t times w2 plus t times w3, this is less than delta. Therefore, this quantity in the brackets, that's going to have absolute value less than epsilon. So we will be able to write this as, hence this is less than or equal to mod of z3 minus z2 times epsilon times 1 minus 0, which is 1. And the second one will be the absolute value of w3 minus z3 plus absolute value of w2 minus z2 times the integral of f of 1 minus t times w2 plus t times w3, which has absolute value less than or equal to m on t bar. So in particular, this is going to be less than m. z3 minus z2 is bounded by the diameter of t, which was captured to be d times epsilon, and w3 minus z3 was less than delta, which in particular is less than epsilon. So this is less than 2 epsilon m, and hence this is less than or equal to d plus 2m times epsilon. Let's now focus on what happens on the other two sides. Integral of f on what are the other two sides? z3 to w3 and w2 to z2. I'll just show you what happens on z3 to w3 of f of z dz. Absolute value of this is going to be equal to some very similar argument as earlier. It's a curve starting at z3 plus t times w3 dt, and gamma prime t is just going to be equal to w3 minus z3, absolute value of this, and that's going to be less than or equal to w3 minus z3 is bounded by delta, which is in fact less than epsilon, and the thing inside the integral will be bounded by m, and therefore the entire integral of f over t, this is less than or equal to some constant times epsilon. Similarly, you can talk about the other fourth side of the parallelogram as well, quadrilateral as well, and we will be able to conclude that this is less than epsilon for every epsilon, and hence integral of f over t is equal to 0. So essentially what we have concluded is that, I have started writing f at some point of time, even though I was writing g, I don't know when it started becoming f. Okay, so from here, whatever is written here as f is actually g. So let me just do that small work. So this is g, I hope that this has not confused you, because our attempt was to show that G is a holomorphic function. So, the Morera's theorem was being attempted for the function G and not on F. It was a silly mistake to have written F here. But I hope it has not confused the proceedings of this proof. Yes, and this tells us that G by Morera's theorem is holomorphic in dZ0R. But our choice of Z0 on the set I was arbitrary, and which tells us that G is hence holomorphic on omega. Therefore, we have a holomorphic extension of F to the entire set omega. This result is classically known as the Cauchy reflection principle, which has really far-reaching implications in number theory and many other fields.